Welcome to Academic Digest class. This question says Gauss' law is most useful for calculating electric fields in cases where the charge distribution is highly irregular, electric field varies randomly in different regions. C. The charge distribution has symmetry, that is, being spherical, cylindrical, or planar, the charge is moving at high velocity. So the answer is C. The charge distribution has spherical, cylindrical, or planar. That is, all those things we taught you about. Is it in linear density, lambda? Is it in surface density, or is it in rho, volume density? Okay, so we moved from there to what we have today. So what we have today is, I want to tell you about charge. Why charge in series is the same. And charge in parallel for a capacitor is different. I wish this to enter here. What the fuck? I want you to enter here. Enter here. I don't want to come down here so that I can give space. But see, it's making it look like. Alright, so if I have, for example, let's say this is a volt. Let's say the voltage is here. Then let's say I have this now to be my capacitor. Can I see? Let's say this is C1. Let's say this is C2. You can see very well that when charge flow, work done, moving charge is volt. So let's say I have on this side plus and minus, on this side plus and minus. And you know that in metals, we always take it that charge moves from the negative side. So if this is the negative side and this is the positive side, as this thing moves this way, it will go here, exit through this way. This is how it will be moving. The stored charge will be moving until what is on this side and this side becomes equal. But let's check something. You see that as this negative charge moves, it will come here, get repelled. As it gets repelled, it will go here, attract. Then it will move again, come here, get repelled. As it come here, get attracted. So you can see it that as it's doing that thing now, the proton that is here, that is like, should I say, heavy, not really moving. As he's doing that and he's pushing it, the proton itself at some point will be moving slow, you know. Then as it comes here, it gets attracted, get repelled, then come here, gets attracted. So if you check it, you see that the charge on this, because this thing is on a line, you see that they're on the same line. So the charge here, if you check it, the number of charge here is plus and minus. Shebi? Yes. Plus and minus on this end. Then the same thing here, plus and minus. So the same thing here, plus and minus, minus plus. So you can see that the total charge here and the total charge here, they are the same thing. So they will cancel out on this. So they will have net charge the same, because what is happening here is happening here. So it's the same thing as saying whenever we have right, left and right hand side together. If you remember when we did charge, where we said that negative, that if I have positive charge and I have negative charge, that it will move this way, and this one now will enter here. So you can see that that direction is going this way. It's going in such a way that charges travel, the same charges travel straight. But when I have a situation like that of parallel, it's not the same thing as saying like I have a charge here. Let's say this is positive and I have negative. It will enter here. If I have another charge, are you seeing it? It will move and enter another one. I seen it. So they are different charges. So this is the situation that is in parallel, because you can see that for parallel, these are two parallel lines now. But once you are talking about series, it's more like this way. And that is why I told you that even when it moves this way and moves this way, you can see that it is still going this way and still coming this way for series. So that is why we normally consider that charges. So we normally say that charge in series is the same, while for parallel, let's say I have something like this now, come here, let's say I have, sorry, I closed it, not me. So you can see that if I have this to be C1, this to be C2, and I have V, so the charge that will happen here will definitely come here and get Q1 and get Q2, because as it moves, it will enter this one. So it's like positive and negative that forms on one line, then the other one negative and positive that forms on another line. So that is why we say that charge in parallel capacitor is different. But notice that once this charge moves from here now, as he enter here, once the voltage, the work that is being done, remember that work being done on a charge is what we call voltage or electric potential. So as it moves to do this work, as it's going here to do this work, it's also going here to do this work. But notice that when it enter on this one to do work, by the time it's enter here, it has done work, move again. So it's almost like it's now moving. So the situation here is like he's moving, he did not move at the same time. So he's moving like from region of higher to lower. If you remember, voltage is moved from region of higher to lower electric field. So for that reason, the first thing it means that he's moving with higher frequency. Then as he's done with this, it is moving to the second one. But when this one moves, you can see when it moves here up to this point, it fills up everything on this one. So if you come here and come here, the only thing is attacking different charges. So it's attacking different charges, and for that reason, the electric field on this, the impacts on these electric fields are different. If you remember, when we did Gaussian theory, we said that if we have this to be a metal, that electric force will not move outside here and it will not move up here. Rather, if this is negative and this is positive, electric field will move this way. I seen it is going to this. I seen it to this end. Electric field will be experienced on this side that runs to attract, which is E. So the same thing here, when it moves, the electric field is going on this one, going on this one. So the charges here are getting attracted, the charges here are getting attracted. So these electric fields are of the same, that is, the voltages on the electric fields are of the same level or of the same region. But for this one, as it's moving, so you can also say that if you are considering just this one, you can see that this is more like that case of series. So I don't know how else to explain it, but just use this now to remember it and now think about it in different angles so that you know that voltage for capacitors in series is different. So while voltage for parallel capacitor is the same. So you need to know that. That's why I have a class on this where we made the video and we took time to explain how to get the formulas. But this one is a class on why charges in series and parallel behave differently.